Okay, so this is going to be part 2 of our, or day 2 of our 2.1 limits lecture. So we talked about evaluating limits by creating a table of values and also graphically by analyzing the graph of the function that we're looking at. We talked about where limits exist, or different examples of when limits exist, but also when they fail to exist. And now we're going to talk about one-sided limits. So all of the other examples we've looked at so far have been two-sided limits, where we want to know what's happening to y as x approaches some value from the left and the right-hand side. Okay, but now we're going to be thinking about one-sided limits. So what's happening to y as x approaches some number from the left side, or what's happening to y as x approaches from the right-hand side. Okay, so this is the same piecewise function that we looked at before, and the limit didn't exist. So I'm going to sketch that graph again. And in the last video I explained how to graph that. So if you need to go back, go ahead and do that. Okay, so we wrote out when we proved that the two-sided limit of this function as x approaches 2, when we proved that that didn't exist by creating the table of values and looking at the graph, let me pull that back, okay, we wrote out as x approaches 2 from the left, f of x approaches 2, and as x approaches 2 from the right, f of x approaches 4, okay? So let's think about taking the left-sided limit first, okay? So the left-sided limit first. Okay, where we think as x approaches 2 from the left. Now, to symbolize from the left, I'm going to put a minus where an exponent would go. So as x approaches 2 from the left, f of x is approaching 2. And in limit notation, I can say the limit as x approaches 2 from the left of our function, f of x, is equal to 2. So the one-sided limit exists here. And our right-sided limit says as x approaches 2 from the right, we put a plus sign, okay, to symbolize as x approaches 2 from the right, we put a plus where there would be an exponent. F of x approaches 4. And in limit notation, this would be the limit as x approaches 2 from the right of our function f of x equals to 4. So the one-sided limits here exist. The two-sided limit does not exist because our one-sided limits don't match up. They're not equivalent. Okay, so the one-sided limit of function, here's kind of the definition, and we just kind of talked about this, so you can read it. And like I just said, or like when looking at that example, for the standard two-sided limit to exist, the left-hand and the right-hand limits must exist and be equal. So you know you're taking a two-sided limit, or when you just hear you're taking the limit of a function as x approaches some number, that implies the two-sided limit. Okay, you have to see that plus or that minus in the right corner of the value a to know that you're taking a one-sided limit. Okay, so let's look at this piecewise function, and then we're going to take all of these limits. Notice we have some two-sided limits in there. We have some two-sided limits in there and some one-sided limits. Okay, so for when x is strictly less than 0, the graph's going to look like negative x, y equals to negative x. So a line that has a y-intercept at the origin and a slope of -1. Then, between 0 and 1, the graph is going to look like y equals to 0, so the horizontal line. And then for x greater than or equal to 1, the graph will look like x squared. Okay. Okay, so looking at the graph, this says the limit of our function f as x approaches 0 from the left. So we can ignore everything to the right on the graph for now. So as x approaches 0 from the right, the y values are approaching 0. So we can say that one-sided limit is equal to 0. Okay, our next limit. So the limit of our function f as x approaches 0 from the right. Now we can see that there's this part of the graph to the right of 0, and there's this part of the graph. Remember, we just care what's happening in the neighborhood, so we can actually kind of cover up everything that's not in the neighborhood of 0 to the right, and then cover up everything to the left of 0. Where we can see that as x approaches 0 from the right-hand side, our y values are also approaching 0. Now, looking at the graph, we can see that this limit is equal to 0, but also because we evaluated our one-sided limits and they match, we know the two-sided limit must be equal to 0. As x approaches 1 from the left, f of x is approaching 0. As x approaches 1 from the right, f of x is approaching 1. Our one-sided limits do not match. There's a jump in the graph that we can see, so we just have to say that the limit as x approaches 1, DNE, does not exist. Okay, now, x cubed minus 5. It's a smooth continuous curve because it's a polynomial function. So we could actually just substitute in this number. This is going to be this first case, even though we're just taking the left-sided limit. We could technically substitute it in, but let's look at the graph. So it's x cubed shifted down 5 units. So I'm going to hit the trace. And instead of typing in a value, I'm going to use my arrow keys to move. I don't know if you guys can see this very well. Oh, there we go. So I'm using my arrow keys to move the cursor closer and closer to 3 from the left-hand side. Oh, let me adjust my zoom. Okay, so we're getting closer to 3. Oh, so here's pretty close to 3 from the left. Oh, now it's going off. Okay, maybe it's not going to work for me right now. But if we substitute 3 in here, 3 cubed is 27 minus 5 would give us 22. So the limit, the left-hand limit would be 22. The right-handed limit, so the limit as x approaches 3 from the right-hand side of x cubed minus 5 would also be equal to 22. And therefore, the limit as x approaches 3 of x cubed minus 5 would also be 22. Okay, or because this is a smooth continuous curve, we're going to have that first case of where the limit exists, and you can just substitute in whatever this x value is into the function. Okay, let's go ahead and look at the graph of 1 over x minus 3. Now, 1 over x minus 3 is the graph of 1 over x shifted to the right 3 units. So that means that the vertical asymptote at x equals to 0 is also shifted right 3 units. Okay, so we have a vertical asymptote at x equals to 3. Now, as x approaches 3, let me just sketch the graph on here so we can get a better idea. Okay, this is where being really familiar with those common functions and knowing translations and transformations can come in handy. So as x is approaching 3 from the left-hand side, and we can even use the trace, if we just keep approaching 3 from the left side, okay, our y values will keep getting smaller and smaller. Hops over because my window isn't large enough. You can see in my sketch graph, as x approaches 3, the y values are decreasing without bound. So we would say that the one-sided limit is equal to negative infinity. Now, the right-handed limit, so the limit as x approaches 3 from the right, of 1 over x minus 3 would actually be positive infinity. Okay, because as x approaches 3 from the right-hand side, the y values increase without bound. So for the two-sided limit of this function, because our infinities do not agree, we can't say plus or minus infinity, we would just have to say d and e. Okay, so this is actually, the one-sided limits here are examples of unbounded limits as well. But if we go back to this limit here, which we took earlier, and we said the limit was equal to positive infinity, we refer to this as an unbounded limit. So this is, we have the vertical and the horizontal asymptote. Oops. That doesn't look so good, but you can see as x is approaching 0, our y values are approaching positive infinity, so they're increasing without bound. All right, looking at 1 over x, we already looked at 1 over x minus 3, so now we're looking at the parent function of that function, vertical asymptote at x equals to 0. Horizontal asymptote at y equals to 0. And we have the two branches Okay, so the limit of the function as x approaches 0 from the left is negative infinity, because our y values are decreasing without bound. As x approaches 0 from the right, we say our limit is equal to positive infinity because the y values are increasing without bound. And this, like the example of the limit of 1 over x minus 3 as x approaches 3, we have to say d and e because those positive and negative infinity, our infinities do not agree. Okay. So there's our definition of infinite one-sided limits or unbounded one-sided limits. Okay, so now we're going to start talking about finding limits algebraically, and something that sometimes happens when we try and find a limit algebraically. So going forward, unless you are specifically asked to evaluate your limit numerically or graphically, you're going to first try direct substitution, where you just substitute the x value into the function and see if you get some finite value. Well, I guess don't do that for necessarily piecewise functions because there could be a jump in the graph. You want to think about the graphs for piecewise functions. But for a polynomial function, which all polynomial functions are smooth continuous curves, you can just substitute whatever a is into the function and evaluate, and it's going to match the limit. If you're taking the limit of a rational function, you're going to take the limit of the numerator, and if you get a limit other than 0, like if you get 1 or 2 or something, and then you take the limit of the denominator and you get equal to 0, you know the limit technically doesn't exist because you're going to have a vertical asymptote at that x value. But the limit could be positive infinity, negative infinity, or if the one-sided limits do not agree, it could just d and e, does not exist. But you have to think about the graph here. If both of the limits of the numerator and the denominator are equal to 0, there might be a limit. But that's something referred to as, or that's a type of indeterminate form. Okay, so if we take the limit of a rational function and we substitute a in for the numerator and denominator and we end up with 0 over 0, that's referred to as the indeterminate form. This happens because there's some sort of a common factor in the numerator and denominator. So we have to try and get rid of that common factor using algebra. Okay, in these next examples we're just going to be factoring, but we have to try and get rid of that common factor and then see if the limit exists or not by trying direct substitution. In section 2.5, we're going to talk about some other types of algebraic manipulations that we can try when we end up with 0 over 0. But for now, they're all going to be just factoring the numerator or denominator or both. All right, our first example. I want you guys to pay attention to how I'm writing out my work. So if we take the limit as x approaches negative 3 of x squared minus 9 over x plus 3, and we try substituting negative 3 in for the numerator and in for the denominator, because the numerator is a polynomial and the denominator is a polynomial. So I can just try substituting in negative 3 in for x for both. We get 0 over 0, which is an indeterminate form. It's one of the indeterminate forms. Okay, so this tells me that there is a common factor, and looking at the function I can see that. So rewriting the limit, okay, I see the numerator factors. to x plus 3 times x minus 3. So x plus 3's will cancel. That means there's a hole in the graph at x equals to negative 3. So this is equivalent to the limit as x approaches negative 3 of x minus 3. This is a polynomial, so if I substitute negative 3 in, we get a limit of negative 6. So the limit here is negative 6. This would actually be an example of case number 3 where the limit does exist. There's just a hole at x equals to negative 3. Okay, so looking at this one, we can see if we were to substitute 2 in for x, we would get 0 over 0. So we have some algebra to do to try and simplify the function. So we can see already this is in factored form, so we can cancel the numerator, x minus 2, with one of our x minus 2 factors. So we'll have the limit as x approaches 2. Now, if I substitute 2 in, from here, I'll get 0 in the denominator. Okay? Thinking about this function, I know what that graph looks like. So if I were to substitute 2 in, we would end up with 1 over 0. Okay? This tells me there's a vertical asymptote at x equals to 2. And knowing what that graph looks like, that's 1 over x shifted to the right 2 units. So thinking about that graph, and what's happening as x is approaching 2 from the left and the right hand sides, right? So the limit as x approaches 2 from the left of 1 over x minus 2 would be equal to negative infinity, whereas the limit as x approaches 2 from the right would equal to positive infinity. Those infinities don't agree. Therefore, we can say the limit as x approaches 2, and we write as our original function, dne doesn't exist. Okay, last example. So, if we were to try direct substitution here, 3, I see the denominator would be 0, but I want to make sure the numerator would be 0. So 3 minus 13 times 3 plus 4 times 3 squared would be 0. So we'd end up with 0 over 0. So let's look, we know that a common factor is causing 0 over 0. So I know one of the factors in the numerator has to be x minus 3. Okay, so the numerator, x minus 3, I know one of the factors is x minus 3. I see that this has a leading coefficient of 4, so this one has to be 4x minus 1. Okay, so there's a hole at x equals to 3. So now we can take the limit as x approaches 3 of 4x minus 1. So that means that this graph looks like the line 4x minus 1, but there's just a hole at x equals to 3. We'd see that if we graph it. Yeah, so we see the line 4x minus 1, and if we hit trace and we type in 3, I don't know if you guys can see that. If we hit trace and type in 3, we get y is undefined. Okay, 4x minus 1 is a polynomial. I can substitute 3 in. So we get the limit is equal to 11. Okay, so you guys had a worksheet that you guys were working on, and then you had a couple problems that were very similar to these examples from the book. To try, there will not be a homework quiz next class. We'll do some sort of a warm-up. Have a nice weekend.